Good afternoon, everybody. Welcome to this Department of Chemical and Biological Sciences lecture series. So today we have Dr. Samrat Ghosh, who is a scientist in CSIR-CLRI, which is Central Laser Research Institute in Chennai. And Samrat will be mostly talking on the charge transport in the photovoltaic hydrogen evolution of two-dimensional porous organic semiconductor. So I request the host, Dr. Pradeep Pachpule, to kindly introduce the speaker. Pradeep.
Thank you, Rajita, and thanks for organizing this seminar also. So it's I'm really happy that Samrat is here, with whom I worked in Berlin also. So it's my privilege to introduce Samrat. Samrat did his BSc from Scottish Church College from Calcutta, so he knows Kolkata better than me, I guess. And he did his MSc from BHU, and after that he did a PhD in CSIR NIST in Trivandrum with Professor Ajay Ghosh. And after finishing the PhD, he joined in the lab of Professor Seki in Quetta University as a postdoctoral fellow. And after, meanwhile, he also got the JSPS fellowship, and then he started working as a JSPS fellow in the same laboratory of Professor Seki. Also, before finishing the JSPS, he also got the Humboldt. So he joined in the lab of Professor Arne Thomas in TU Berlin, where I was working at the same time when Samrat was joining. But he's always been privileged with like getting one extra thing in the hand when there is one existing thing in the hand. He also got the scientific position in CLRI meanwhile, and then he stopped Humboldt, paused Humboldt, and then he joined as a scientist in CSIR-CLRI. So, and now he is currently working as a scientist there in CLRI itself. Besides, he has got a lot many awards, and some of them are he got a Humboldt Fellowship from Humboldt Foundation. He's also got a JSP's Fellowship. Also, he has got a SASIR's Best PhD Thesis Award from Chemical Sciences, and also he got the DST JSPS fellowship also for the exchange program. And there is a list of other awards as well, but I won't go into the details. And with this, I would like to invite Samrat for the talk on why charge transport is pivotal for the photocatalytic hydrogen evolution in 2D coherent organic frameworks.
Thank you, Dr. Am I audible? Yes. Yeah. Thank you, Dr. Pradeep, for giving elaborate introduction. I thank Dr. Rajiv, the HOD of this department, for giving me this opportunity to present the research what I have done previously and what I will be doing in the future. Today's topic mainly discuss on the why charge transport is pivotal for the photocatalytic hydrogen evolution in two-dimensional porous organic semiconductor. Before going to that, I'll introduce my institute and when I'm working. So it is CSIR-CLRI, as you know, it's a Central Laser Research Institute. Although its name implies that it's a laser research institute, but we have a chemical science division where inorganic and basic inorganic and physical chemistry, polymer chemistry, and advanced material organic biochemistry and different kind of basic science also explored. I basically work in the inorganic and physical chemistry section, and we have almost 100 PhD students in this department in the whole CSIR-CLRI. Along with the basic science, we also do the industrial research related to laser and give sustainable laser solutions and development of laser products and their management of the laser waste. Basically, I am a functional organic material chemist where I develop different kind of pi conjugated materials and organize them in different fashion like supramolecular polymer or in the covalent organic framework. So here we can arrange these kind of molecules where initially molecule has some property which can be enhanced or tuned by arranging them in a particular organization. So here you can see the small molecules can be arranged in a two-dimensional fashion where the molecules are stacked one upon other. Similarly, these molecules have supramolecular polymer. As you know, these are the non-covalently linked polymers. So they are attached by non-covalent interaction. So if you try to make or break them, you can make and break them easily because there is only van der Waals interaction. But if you want to keep it stable for a longer time, you should move to the covalent organic frameworks, where covalent bond is the most strongest bond among different kind of bond. So it can stabilize this system, and you can get a framework structure where you can accept several exotic properties which cannot be obtained in other form. So why today's presentation I told you the photocatalysis and the production of hydrogen. Why hydrogen is important? I think I don't need to discuss this. Everyone knows this global energy crisis scenario and how much renewable energy sources we have. So why we should look for a sustainable fuel is that which the way we are consuming the present energy resources will be soon consuming complete energy resources available in the earth. So we need to look for some fuel which can be very much sustainable and doesn't give any environmental pollution. So here you can see due to the rapid consumption of the fossil fuel, we are seeing the environmental pollution and global warming. So what kind of the renewable energies we can see around us? The solar energy, wind energy, and hydropower energy. Now the question is that solar energy in India or in the foreign countries is very different. Even in the Chennai and Kolkata it is different because in Chennai you can get a sunny day almost 200 to 300 days in a year, but in not in Kolkata you can get that much day. So if it can harvest its maximum also, it won't be enough to survive in the whole year. So similarly, some places will have strong wind, some places will have weak wind to rotate the wind turbines and get the wind energy. Similarly, some places will have rivers and other things. So how to store them? So this can be stored as the chemical fuel, which can be used later without environmental pollution. So that is why the importance of hydrogen comes. So hydrogen is basically zero emission energy carrier, which can be processed in this way. So you can use different kind of technique to produce hydrogen, and it can be used for different kind of application, from the ammonia or fertilizer making to the running your vehicle, powering your house with the electricity, everything, and using a fuel cell. So this can be the ultimate solution because once you get the solar energy or wind energy, you can convert into the hydrogen and you can transport in different places and then you can use it. Now, what are the conventional method to produce hydrogen? So you can see these are the conventional method which steel industry is using, the steam reforming method. Now, in this method, you can see the CO is a byproduct, and all this process you can see CO or the CO2 is the byproduct. So if you use CO or CO2 as the byproduct, if this is not the sustainable source or sustainable pathway to produce hydrogen. So we should look at the process where the hydrogen can be produced much greener way. So that's what the green hydrogen, where you can split the water, which is more abundant in this earth, and you can use the sunlight, which is also abundant for at least next 1 billion years, and you can use it using electrocatalysis or photocatalysis to produce hydrogen. So these are the basic process involved in the photocatalysis. So what happens when sunlight falls into a semiconductor? The exciton generates, and exciton eventually gets separated, and the separation, exciton separation, takes place in different material in different fashion due to their different dielectric constant. And this electron can move to the surface based on the material, how much charge carrier mobility it has. It will go to the surface and it can reduce the hydrogen into the H2, or it can produce oxygen. So this basically it involves three fundamental processes. One is the light absorption, exciton generation, and exciton splitting and moving to the surface and do the surface reaction. As you can see, the water splitting, the delta G is almost 237 kilojoule per mole, so it's a thermodynamically uphill reaction. So you need to be very careful to get good efficiency because once you get the sunlight, there will be several processes which will be decreasing the efficiency of this hydrogen production. For instance, the recombination of the hole and electron, and other trapping of this hole and electron in different places of the semiconductor. So very first photocatalysis was done by the Baum and Rehman in 1921, as per the literature reports suggest. So this is a German paper. Basically, it's an attempt to fertilize the water, and you can see they have used AgCl and light, then KCl and light, and they can produce the hydrogen. Almost after 50 years later, Honda and Fujishima, everybody knows about this paper, and they have used the photoelectrochemical setup to produce hydrogen. So here they use a platinum electrode and a TiO2 electrode as a photoactive electrode, and then they excite with the light, which produce the electron, and electron goes to the platinum, which produce the hydrogen. Now, after that, almost the chemists started exploring different kind of material, not only TiO2, different types of material, and they explored almost most of the periodic table elements and produced different oxides, sulfides, nanoparticles, and other things for the water splitting. So this all this material has very different band gap, and based on their band gap, their efficiency changes, because the driving force for the hydrogen evolution. So you can see, suppose for the zirconium oxide, the band energy is well above the hydrogen at a particular pH. So it can very easily give its electron to reduce the hydrogen. While if you see the TiO2, it do not have sufficient gap, although it can do it, but this will be more fertile than this one. So this they have tuned the band gap in different way to harvest maximum light and play with the driving force to reduce the hydrogen. Parallel to this inorganic semiconductor, conventional inorganic semiconductor, people try to use the organic material. Why organic material? Because nature generally use photosynthesis. And photosynthesis is an organic process where we use porphyrin-based system, which can act as a light harvesting unit, and it can do photosynthesis very efficiently. So, so people started moving from the inorganic semiconductor to the organic semiconductor just to explore this one. And also, inorganic semiconductor has one typical drawback, is that you cannot change much this band gap like organic material. In organic material, you can just take suppose this system, you put another benzene you can tune the band gap. But in this case, if you do only, you can tune the band gap, but not in very great extent. Due to this kind of tailor-made synthesis and properties, the organic material got very much attention from 1980s. So initially, molecular photocatalyst was used, then linear polymers has been used, then supramolecular polymer used, and graphitic carbon nitride and conjugated microporous polymer. So these are used, and one thing common in this one is that they are almost all a conjugated system. So because of their conjugation, they can harvest the light, and the electron, the exciton is generated, and then gets treated as I explained in the previous section. Later, very recently, almost in 2011 or 12, people started using this another class of material, which is known as covalent organic framework. So here we have introduced the conjugated microporous polymer, which are polymer, but they are not framework. So the basic difference in between the porous polymer and porous framework is that it has a well-structured frame where the ligands are placed in a particular position, and it has used for gas sensing and separation, membrane drug delivery, various applications. And Dr. Pradeep is here, and he has various expertise in this kind of material. Almost 10 years is working on this material. And this material can be synthesized very easily by just taking the ligand with the particular geometry. If you take suppose a linear one, and you can condense this one in a hexagonal fashion. So if you take a trigonal one with a particular angle, you can get also a hexagonal one. Similarly, trigonal with a ditopic ligand, you can get hexagonal. Tetragonal thing with ditopic linker, again you can get tetragonal one. Kagome lattice. So whatnot, different kind of arrangement you can do. By arranging the chromophore in different fashion, you can really tune their property, band gap, and efficiency for photocatalysis and other applications, which I will be explaining in the next slide. So these are the basic chemistry. This is the first chemistry used, where boronic acid condenses with the catechol kind of system, and then boronic ester form, and it can form a crystalline framework. But this is very much susceptible towards the water. If you calculate the delta H for this reaction, it is zero. Basically, there is no change in the delta H during this reaction. So this kind of linkages are not very stable. So people started looking at the more stable linkages like imine. Problem is that while you are constructing this one, there will be a lot of defects, which defect will be not allowing you to get a very crystalline form. So you should introduce some kind of chemistry which can rectify your defect. That is why this kind of dynamic covalent chemistry has been used, which can break and make during the process. So generally, this kind of synthesis takes 3 to 7 days for the synthesis, where while the reaction inside the matrix, some bonds will be broken. Here you can see the bonds will be broken, which can eventually during the reaction rectify itself and form the crystalline lattice. So that is why we use generally the dynamic bonds, which reversibly can undergo making and breaking of this system. Later, this kind of beta keto also has been introduced. So initially formation of the reversible system, then followed by locking of this system by beta keto. And this chemistry has been introduced by Professor Rahul Banerjee, who is working in Kolkata. And this is a very popular chemistry to construct this kind of material. So this one, what I tried to explore this material as the porous organic semiconductor. So as you know, all the semiconductors are mainly non-porous. Now, what kind of advantages you can get if you get a semiconductor with porosity? So you can do different kind of sensing application. You can get a lot of active site where you can do the catalytic processes and other things. So the first report on the POP as the photocatalyst has come in 2014 from the group of Bettina Loos, and they showed these are the potential material for the photocatalytic hydrogen pollution. And later they published a review where they have mentioned this kind of material has challenged how to do the photocatalysis because it depends on several factors. So not only of material, it's general for every material. It depends on several factors. For instance, like I told that linkage stability. If it is not stable, how can we do the catalysis? Robustness of the top, stacking and crystallinity. Suppose this case, in this case, you can see two layers are stacking one top of each other. What will happen if they don't stack one top of each other? They stack in this way, which is A stacking or AB stacking or different fashion. Similarly, the axial charge transport in this direction or in this direction. Porosity, how much porosity is needed basically. If you keep increasing the porosity, will the hydrogen evolution increase linearly or it saturated after some time? So this kind of question we started asking ourselves, and we thought, how can we address that? To address this one, I made an attempt to take all this issue in one POP system and try to investigate. So here you can see we choose 4 different linkers where we have used anthracene, and this is an benzothiazole system, this is benzene, and this is triazine system. Basically, what I tried to keep the length is same. So what if I keep the length same, they cannot understand which is the which linker, which I will be showing later. And this is the electron rich system, and this is the electron deficient system. So we try to change the electron rich and deficiency, so we can make a donor acceptor system. As we know, because of the donor acceptor, the molecular orbitals get MO diagram, so we can see the band gap will be decreased. So you can tune the band gap by just changing this unit. So you can see when we make this cup, this different cup has different color. It shows that they have different band gap. Now we try to understand their structure. So if we synthesize this material at 150 degree, we get one product. If we synthesize at 120 degree, we get different product. So that we have understand from the pH pattern. So here you can see The anthracene-based COP, when we synthesized at 150 degree, it is in the peak side is like this, whereas in 120 degree it is quite sharp. So if we simulate this XRD with the simulated model, we can see this is the AB packing, this is ABC packing. AB packing is nothing but when this is AA packing, this is AB packing, and if the third layer is a different way, then we call ABC packing. For the other curve, we can get AA packing at 150 degree. You can see all the case AA packing, and other at 120 degree, we can get the AB packing. Now, one question we asked in the first slide that how the packing affects the hydrogen evolution. Second question was the how the porosity affects. Because we changed the packing, the porosity also changed. So here you can see the POC prepared at 120 degree has always lower porosity than 150 degree. So so if we compare, although their band gap is similar, which I'm coming in the next slide, but their porosity is very different. Now we can understand from this one how porosity is affecting the hydrogen emission. Here we have analyzed the optical properties. There you can see the curve synthesized at 150 degree and 120 degree have almost similar band gap, which is presented here. So this is 150 and 120, almost 2.4 band gap. You can see similar, but their band position is slightly different from each other. In case of the TZ curve, you can see they are well below the hydrogen reduction potential. Now, from this analysis itself, we can say this will not give any hydrogen because they don't have any driving force, which I was talking. Here you have sufficient driving force, but here there is no driving force. As we expected, this doesn't give us any kind of photocatalytic activity. One thing I forgot to mention is that the torsional angle also we played over here. Because of this unit, here the torsional angle is 66. Torsional angle means the middle part and the side part is kind of something like this. Now I can play around this kind of torsional angle like this one. So first one is quite a perpendicular manner with the 66 degree. Sorry. Second one is slightly lower, and if you go to the TZ one, it is almost flat. So two units are completely flat. This is basically affecting this kind of packing fashion. So when one layer is non-planar, another layer is planar. So planar will sit one top of each other, but non-planar one will feel some kind of steric repulsion. So say they try to repel and prefer this heavy kind of stack. So then we analyzed the hydrogen evolution, and we found this BT curve gives the maximum hydrogen evolution under the visible light in comparison to the other curves. Although BT curve has not the highest porosity, you can see the BT curve has similar porosity with the AMT curve or the TP curve, but the hydrogen evolution is so high, and they are quite low compared to that one. We tried to investigate this one. What is the reason? So is the porosity is the factor, or the packing is the factor, or other thing? So we have analyzed all these things here. So these are the 120 and 150. You can see this is the torsional angle presented here. This is the porosity. The BT curve has only 550 meter square per gram porosity, whereas TZ curve has 1490. But it doesn't have the sufficient driving force. That's why it could not able to do the photocatalysis. TP curve has 600, but still it is lower than this one. Then we have to look at the other parameter. So what is that parameter? Here you can see the band gap. So BT curve has the band gap of 2.1, whereas TP curve has band gap of 3.6. So that means 2.1 will have this more solar energy than other TP curve. But will this one affect the hydrogen evolution in that extent? Because BT curve 120 also has the similar band gap. That is also crystalline, but the packing is different in like AB packing. This hydrogen evolution rate is 750, while others are quite low than this one. So we need to look at some other parameters. So we look at the photoconductivity. As I mentioned, after the excitation, there will be exciton, then it will be split, and then it has to go to the surface. So to go to the surface of this photoelectric reaction, it should have good charge transporting property. BT curve has good charge transporting property compared to other curves presented here. Also, from the EPR, we can see there are sufficient charge carrier generation in case of BT curve because of the splitting of the exciton and charge transport. and which reflects here that due to the high charge transporting property, only Betic of giving the very high catalytic activity. So here you can see too, we have tried to understand this is because of the electron or hole. So we put ammonia and SF6. Basically, SF6 can scavenge the electron, whereas ammonia can scavenge the hole. And you can see the Betikov is basically the electron transporting material and can do the hydrogen regulation. Further, we have done this is just a pictorial representation. Further, we have done so our best copy is the Betikov. Now, if we try to introduce the ANT, because as you remember, in the initial stage, I told that they are having the same linker length, so I can replace it. They cannot identify. I just mix it, they will be replaced one or other because they are having similar length, so the lattice constraint will not come. So in BTCOP, we try to mix all other things and try to tune their band depth. What we found is that BTCOP still is having the highest photogalactic activity. If we mix also, the mixture is less. Now, why it is less? Because the charge transport happens in this direction or in plane direction. We don't know which direction it is happening. But the another material act as the impurity in this case. This kind of units act as the impurity and just stop the percolation path for the electron or holes to travel to the active center of this catalysis. So that is why the BTCOP is the best among others. So from this, all this experiment, what we conclude is that porosity is of course the important factor. Cracking, crystallinity, and all others are very important factor. But one of the major factor is that intra or interlayer charge transfer. If you increase the porosity from 1000 meters square to 2000 meters square, you may not get the hydrogen evolution in twice. If you increase the stacking also, you may not get the your performance in a very high amount of increase until or unless the stacking is affecting the charge transport. But if you increase the charge transport from 1 to 2, you may get the hydrogen evolution almost 10 times. So this kind of observation we got from this result. All these combined parameters are important, but charge transport plays one of the important factors in this kind of catalysis. Later, we just did an extension of this work. So here, the torsional angle is this 360. So it's something like this. Now, how can I make it planar? So we just put a triple bond over here, and we can get a planar system. And then we can arrange them in a Kagome lattice. We know Kagome lattice can give some kind of exceptional property due to the arrangement of this promo code in different places. And also, this is a planar system. We used this unit, which I mentioned, beta dynamic. Whereas, when if you use this triformyl derivative, it's a non-planar one. How this planarity will affect the optoelectronic properties, which we'll discuss here. Interestingly, this COF, when we synthesize, we can get it as a film. Basically, COFs are insoluble powder, which I showed in the initial slide. The powder, it cannot be processed like any other material. If you try to take a small molecule, you can create a very good film. But in case of COF, you cannot do such thing. It's just a powdery material. So to make the film, you need to use different kind of method. And in this case, you can get very good film, and you can transfer over different substrate, or you can grow in different substrate. And this COF has very good crystallinity, which is emitted from the GIXRD. And you can see the hexagonal lattice here, you can clearly seen under the cryo-TEM. Then we try to understand their optical and electronic properties. From the absorption spectrum, it shows that it has a band gap of 2 eV almost. And so if you excite with the light, there is a chance to generate the exciton, and which eventually will split into the free charge carriers. And how these charge carriers are moving, we have tried to prove that one. So we have measured the photoconductivity using time-measured microwave conductivity. And you can see here, after the exciton generation, this the free charge carrier is in quite a large amount than previous one. So previous the signal was very faint. In this case, the signal is quite strong. And we try to do the temperature dependent this time measure microwave conductivity, and we can see the activation energy is almost 14.3 milli. As you know, the room temperature is almost 25.6 milli. So this exciton can break into the charge carrier in the, even in very low binding energy is there. So this plot shows that the different temperature affects the conductivity in different extent. So initially we can see from this plot there is very minimum slope. So it shows for the, as you know, there is two type of transport. One is band transport, another is hopping transport. Now in case of hopping transport, there will be several tracks where once you excite the electron will be hopping one to another with the thermal energy. But in the case of band transport, because of the phonon, you may not able to transport the your charge carrier in the higher temperature, because there will be phonon vibration and the phonon scattering will come into the action, and you see the decreasing the charge transport with increasing the temperature. And here we have calculated the charge carrier generation yield, and from that we calculated the conductivity. And you can see for this system, with the decrease in temperature, we can see the increase in conductivity, and also it has a good photodetector ability. So if you take this film using a 2-meter digitated gold detector and just shine the light, you will see there is a increase in current by shining with the, even with the room light. To understand this charge transport, we calculated the band diagram, and we found in plane it has a band dispersion. And if we calculate that, the reduced mass will be almost 0.64 m0, whereas in the out of plane direction there is no almost no band dispersion. So the electron will be heavier over there. Also, it is supported by the homolumo calculation, where you can see that it is highly conjugated through this chain. And here is the calculation for the other one, which is non-planar. In case of planar, you can see large band dispersion, but in case of non-planar, the band dispersion is very slight. So that is why that has lower photoconductivity, and it has the localized HOMO and LUMO. That is why we see very low photoconductivity in this one. So finally, we use this material for the hydrogen evolution, and as we have expected, this material shows very high photoconductivity activity, which will publish soon. And we are looking into this kind of details more, how to improve the charge carrier mobility in kind of pop system, so we can get better exciton separation. So first we can look into the exciton binding energy of this material, and then this, so we can display. As you know, the organic material has very low dielectric constant. Because of that, the exciton is very well highly bound, and if we can separate it, and if it is having good charge transporting property, it could give very high photokinetic hydrogen evolution compared to others. So these are my previous mentors and collaborators, and I thank all my funding agencies, and thank you for kind attention. And if you have any questions, I'll be happy to answer. Thank you.
I have a question. So you said that the Torsional angle is different, and that actually changes a lot of chemistry. So of course, we change the planarity. Uh, we think that that is also affecting on charge transport. If motive is like it's not planar, yeah, then it's like it cannot transport the charges very efficiently. Sure. As soon as it's like more planar, it will be more like three paths in a way. So, but how do you look at that?
Yeah. So from this, it's a little bit clear. So here you can see continuous calculation part for the chart. But if the anthracene is in non-planar position, then the anthracene for any unit will have a localized HOMO unit. The localized HOMO, there will be no calculation part, so it will act as a tracking center, so you may not get good transporting property. So that is why the non-planarity plays a crucial role for this kind of material to give good transport.
And the second one shows you have a mixed forms.
Yes.
So in this mix form, do you know the like percentage or it's just random?
Yeah, it's percentage we know, but we don't know the location where it is.
Yeah.
Because initially we are taking the ligand, suppose I take 90 is to 10. So we know the percentage of the ligand, but we don't know the location.
It could happen at one point that one ring is made out of like the previous common synthesis.
Yeah.
It could be mixed, it could not be mixed.
Yes.
And what this material is?
This material was quite good this time, but we can moderate this time. But there is patient was there, and we can assign that the packing of this one from the simulated video.
I have a question.
Sure.
Why these molecules are making silver?
By this,
Molecules are making silver.
because now they are having a conjugated framework method.
But they could also be, make other kind of conductors.
Yeah, but in this case, there is not sufficient charge scale. The number of charge carriers are very, very less, and their band gaps are quite high, as you can see.
Yeah, the
More
band
than
gap.
yeah.
The band gap comes when you have silver. Now, why is band gaps at all applied? Because in the other like MOAs or CO, they are at all conductors. Probably they are conductors.
No,
No.
Till now,
So their band gap is very high.
yes.
So what makes these band gaps coming together? If you say two materials, like say, so their band gaps are overlapping, so they are conductors. So what makes these molecules arranged in such a way that their band gap is within the semiconductor?
Like conjugation is bringing it
But
all
conjugation makes it conductor.
Yeah, but if you look at this one, so here, if you see
Like dye molecule.
see this
Just
is
like
the
dye molecule. Dye like molecule is just
They are stacking also.
exactly this molecule. Suppose if I take this ligand, ligand will have a band gap of 3. Suppose. But when I make this material, then it will reduce to 2 because there is increase in the effective conjugation. Now there is a question: how much effective conjugation is it? How long? As you know, polyacetylene has a very long conjugation, but in this case, I don't think because of we have such a extended conjugation, still the conjugation length is not long. If it is highly conjugated, then we could have get very low band gap. But in this case, the conjugation is not that much extended, and the effective conjugation length is not measured.
So there are so many errors in the material.
Defects.
Defects and errors. Still there are like planes are not capped. So mobs are in general, I guess they are more
Single
complex. So the band gap will be even less in this case.
Yeah.
In these cases, like, you can clearly see that there is decrease in the band gap. You can see a more crystal material.
But band gap will be fine for a pure material. And then this,
Yeah.
if these are defect, then you will have some defect
Yeah.
sites in
Yeah.
between.
Yeah.
One question, why they call them covalent framework? Why not covalent frame?
Remote conservation.
And how big the frame we can make?
That question can be answered because in this case of we don't get much single crystal, but some single crystals are important. So here you can see the 100 micrometer single crystal. Now, if you know the 1 pore size, you just divide that one. You can get this much number of repeating units are there.
Micron size particle.
Yes, yes.
Why this film is forming?
This film is forming because of the surface and the top interface. So there is we do this synthesis inside a vial. Now the vial wall is the glass wall. Now the solvent and the ligands are there solid initially. Then they started polymerize and they start sticking on the wall. After a certain rate, the film has sufficient thickness, it started detaching from the wall. Basically, it is kind of interfacial synthesis. You take two solvents, also you can get this kind of polymer, or you can water air interface you can use or the sticking property of the reject.
Maybe some lights are there inside the two frames.
Sorry.
Like lots of lights are also there.
Mhm.
They can also join two frames of covalent frame.
Okay.
In that way, they can make also some handle series.
Okay. If your question is something like I have a covalent framework here, I have a covalent framework here, and they are joined together. That kind of thing also possible. Some people use dynamic chemistry, like you take this end with a certain group and this end with another group.
Lots of lights are black and white.
Yeah.
Sumo.
So,
So they are stacked on top of each other. They are sucking.
yeah, so in that case, it is possible to. I could, but thanks for the question. I'll think about that on why not they were not friends.
Can you get some PL from PL from this?
Yes, we can get it. Till now, the PL is not more than 20% or 30%. Average in average, this PL costs are not much anything, but certain costs are important. They are important.
If there is toxic in the
Not like quantum dots. Still, if you do the colloidal synthesis of the core, although some kind of photonic activity has been reported, but the optical changes like you see in the colloidal gold nanoparticle or other things, you won't find in this kind of material. That's also one of my questions. Why, if I take a molecule and assemble them in a very few nanoparticles, why I don't see quantum data there? But if I take a quantum dot with cadmium cylinder, that's something I get. Similarly, carbon dots even, we get it. But if we make the four dots, just imagine. But we made it, but we don't see quantum. This is the interesting thing to look in, but I don't know that. Although I have experimented it actually. Yeah. For carbon dots, the emission can be poor. Yeah. So,
So, I have query. In your case, BT something molecule is the most active one. Yeah? So, this is due to the electron transport or charge transport. So, why this molecule has higher charge transport than others?
others. So, first I'll just take you to the structure. If you see this structure, this is a kind of a donor electron rich. This is the electron deficient. This is the electron rich. So because of the donor acceptor structure, it has lower bandwidth. Okay. And the second thing is that this can stack over one top of each other in AFS. Now you can tell me that this also stack over another, but this is because of the donor acceptor nature, the charge when it generates the exciton, that can be because of this donor acceptor uh, uh, charge. Because donor will be delta negative and acceptor will be delta positive. Yeah. So in that way, your charge gets separated. But here, the charge separation will be difficult.
So, coupling constants should be like higher for that.
The coupling constant between these two, or when you are talking about the transfer integral?
Yes.
So I have not calculated, but if you use the ADF to calculate it, probably it will have the higher transfer integral to the homo interaction. Probably. I have not calculated. That's a good suggestion. Thank you.
How can you increase the crystallinity of the material and how, like one material is less crystalline?
Yes.
And how does it affect your transport and then the hydrogen?
Yes, yes, we have done it. So you can see this one here. If you see, look at the crystallinity. This is the most crystalline one as CBS. Similarly, when we went from this system to other one, you can see that this one huge improvement. So it reflects in the hydrogen. Now we have tried to prepare this material in different conditions where we've got different crystallines. And we use for the hydrogen release. And we can clearly see with the increase in crystallinity, there is an increase in the hydrogen release. Now it is only because of the crystallinity or inside something is there. But, I mean, it doesn't touch.
Like a method of synthesis, how you make
Yes,
it.
you can tune it. You can tune it. Very by synthesis, just by changing the condition of it. You can play around a lot of things because here is the solvent condition. You can use any solvent. Now you know the number of solvents are very high. So one person can go on synthesizing this material. That is why nowadays people use robot to synthesize this.
But this also looks like a honeycomb.
Yeah, it's a honeycomb with the arrangement of the answers in the album.
Kagome is fantastic.
Yeah.
Because this good band structure.
Yes.
There's a flat band.
Yes,
That
yes.
is quite flat.
Yes.
Which is the basic feature of this Kagome lattice.
Yes, yes. There is a paper, there's a fragment structure in graphene kind of system they have done.
So it's due to that
Yeah, yeah.
Kagome
That-
structure.
Yeah.
And so. But this looks like your Fermi energy is like your flat band is just at the Fermi energy.
Yeah.
So if you could slightly shift it
Yeah.
by any means,
Yeah. Doping will be on.
but you could then have a metallic system as you were asking.
Yes.
Why it is the same thing?
I have tried that one, but the metallic conductivity I have not get. I have doped it and I got 10 to the minus 2 is in that fund. Not metallic. In a way, have not. One main problem is the effective computation. The means of experiment.
Because there are examples in organic systems like if you have like um, TTFTC, any kind of charge accepted donor, then you could even get superconductivity.
Pressure,
Yeah. These also show some very good quantum.
yes. So our basic aim during my whole part aim to get such. Unfortunately, I have not get, and I think more than 50 or 60 cops I evaluated. Only this one showed some signal in that instrument. Actually, we will get important. So with that,
And also, you told that some 14 millielectron volt. No? That
yeah,
what
yeah,
was-
yeah,
what was that
yeah,
value?
14 millis.
This is what? This is the exciton to separate.
No, this is
electron.
not excited binding energy. You are pulled down. This is the activation energy for the charge to form. That is very clear.
So at room temperature, then it should be like very metallic.
Yeah, because you have your 20, but it's not metal. Because the number of charge carriers we have tried to calculate using this.
But have you ever tried to make a film and just do two terminal
This is
resistance?
So you put a go home electrode and then place the film over that one and we apply the voltage and try to measure the IU.
But have you ever tried to vary the temperature?
Yes,
And
we
see.
have. We have varied
So
that
how does it?
we have varied that temperature.
No, like with temperature, the resistance, how does it behave? Like a metal or a semiconductor?
Simple, not metal. We went up to
Because you
the
have a
yeah. Even we went to the 4 kV. Nothing. We are
But
just
you-
seeing the resistance of the wire. Yeah. Yes, Arun.
You are changing the temperature. Same time you are changing the light. Means, you are illuminating the light.
Yes.
So there are two perturbations. One is that temperature you are applying, and another one means light you are applying. So then how do you measure this activation energy? Means you have to either you have to do means you have to increase the temperature and you have to measure the resistance. Then only you can do that. Right? Okay, if you look at that equation that I just explained.
Yes.
At the same time, you are changing the temperature and also the light.
Okay.
So then how do you measure this activation?
This light we are putting the same amount of light. Number of photons each time is same. So every time what you do is
That
we
means
make
that intensity you are not changing the
it's not. Yeah. So what we do is effective and X-ray with the same measure. Just we are passing the nitrogen to make the and measuring the temperature and each time we are measuring the conductivity.
So because this is a semiconductor material, generate carriers your humidity may
Yeah,
drop,
like, yeah,
and then you are changing.
yeah, yeah,
And another thing is here,
yeah.
along y-axis you plotted the current. Is it the total current or photo current?
Photo.
This photo current.
Photo.
So what is the responsibility? Means
Yeah,
once-
it is not up to the mark, and that is why we didn't. So this responsibility, if you calculate with the graphic kind of system, but among the COPs, it is one of the best at one item.
and in another slide you have shown some sensing applications like ammonia and
Yeah, that is basically, yeah, it can be sensitive also considered. Yeah. So
yeah. So my point is means whether this crop is means can you regenerate this crop once that ammonia is absorbed?
yeah, this is quite stable.
Yeah, means once it is absorbed, so how to remove that ammonia?
This just pass nitrogen. Ammonia will leave, or you just heat it. If even in that case, if it is so selective to the ammonia, just binding, but they are binding with the non-polar. So we can delete it.
One problem is for organic molecules is actually not stable. Also. There are many like porphyrin, calcinin, they're not stable. Means
Office builds. The stability, that's for my understanding, stability is the same as perspective, right? So, like, how much stability you are talking about? 2 seconds or you want to
obviously for
longer
like,
time?
yeah.
So, if you see the porphyrin is unstable. Yeah, nature is porphyrin. Yeah, quite safe. We also make several porphyrin back.
But no, what we have seen that let's say if you deposit metal calcine in one substrate, and after few days, let's say if we perform some experiment, and if I expose that picture to open here, and after few days if we perform the same experiment, so we are getting actually some degraded result. Okay. Some from that perspective,
Yeah,
this is the
some of
organic
the
material.
porphyrin are not stable. But in this case, we take choose the system in such a way that it will be stable under the water because it has to do 120 hours of photocatalysis. If we have run the photocatalysis for 150 hours, constant, we have not stopped. It's what. Of course, the XRD is getting changed because the system is keep on stealing and the photo light is some decomposition is there, but not very strong.
Did you check that one? Means after the photocatalysis experiment, did you check the crystalline and other parameters?
Yeah.
So is it exactly same or it's
Eventually it is different. On a image paper.
so then how many times you can use that mixture?
Yeah, so that I cannot tell because I have not done
In
that
percentage,
experiment.
let's say for the first round, if you use the second time.
Cycle.
Yeah, yeah.
No, then it depends
Cycle, what we are doing
Going for 150 hours. That means like almost like 6 days, 7 days.
no, no, after performing the experiment, let's say. Before the experiment, you measure the XRD. After performing the experiment, photocatalysis experiment, you collect the sample and you take the XRD.
Yes.
So yeah, what I'm asking means how the
It
efficiency
will
or
be decreasing, depends different comp. Different comp has different increase. But the good thing about it is that you can regenerate it with it. Just if your mistake got decreased, you take this condition. Okay, just add this solvent with that powder and heat it for 2 days or 1 day. Again, you back to that to same. So regeneration is very easy by using this kind of. Now the solvent just a few ml of solvent.
So, any other questions? Any questions from the online attendees?